So we're now going to try to apply some of the properties we've learned, in particular linearity and time shifting, so as to try to determine the Fourier series coefficients of the signal that you see on the screen here. Of course, one of the ways you can do it is directly by applying the analysis equation, and I'd encourage you to do that on your own. What I do here instead is just to use the properties and some of the things that we've learned already, in particular, an example that we've done already earlier. So what we observe here is that it's actually a square wave, except that the square wave has been shifted in time as well as in the amplitude. We're going to use a previous result. So we're going to try to relate this square wave with this square wave, which is something that we did earlier already. So if you, I mean, so what are the Fourier series coefficients for this? Let me go that out a little later. What I'm going to do instead here is going to try to relate what g of t is as a function of x of t. And once again, the reason why I'm doing this is because we already know from a previous example what the Fourier series coefficient of this signal is. So if I can find a way to relate this to this, I can use then the properties of the Fourier series analysis that we've done earlier to try to determine the Fourier series coefficients of g of t. So g of t, if I were to write as a function of x of t, I observe that g of t is actually equal to, if I shift this x of t by 1 second to the right, I'm going to get something of the sort, except that it's going to stay above 0 all the time. And mind you, so one of the examples that we did earlier, this height was 1. So g of t can be related to x of t as x of t minus 1 minus half. So this is something I've demonstrated here. So this is x of t minus 1, which is just a shifted version of this signal by 1 second. And then you clearly can see that g of t with x of t minus 1, the only the difference is that g of t is actually just this signal shifted by half a volt to the bottom, so half of an amplitude to the bottom. And therefore, the conclusion really is so g of t is just something that we're interested in finding the Fourier series coefficient of is actually equal to x of t minus 1 minus half. So the next thing we'd have to do is try to determine what the Fourier series coefficients of x of t minus 1 are. And if you recall from one of the earlier examples that we've done, so this is a general square wave x of t, which is equal to 1 from minus t1 to plus t1, and the amplitude is equal to 1. So this x of t that we had earlier, this x of t is pretty much the same as this, except that t1 is actually equal to minus t1 equals plus 1 and t equals 4. So let's just evaluate what these Fourier series coefficients are going to be for our particular case. So if this is figure 1, so when t1 equals 1 and t equals 4, as they are in figure 1, the Fourier series coefficients turn out to be equal to a sub k is equal to t1 by t, which is just half whenever k equals 0, and assign k omega naught t1. Omega naught is 2 pi by 4, and t1 is just 1 divided by k pi, which is therefore equal to sine k pi by 2 divided by k pi whenever k is not equal to 0. So these are the Fourier series coefficients for x of t. Um, so 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 g of t, as we saw in the beginning in the screen above, is equal to x of t minus 1 minus half. And the Fourier series coefficients of x of t are these AKs that you see up above. And based on the time shifting property that we've done already, what are the Fourier series coefficients of x of t minus 1? X of t minus 1 have Fourier series coefficients, which are just these AKs multiplied by e raised to power minus j k omega naught times t naught, but t naught is equal to 1. So there's actually a 1 here. And omega naught is, of course, e raised to power minus j k. Omega naught is 2 pi by 4, which is pi by 2. So you just have pi by 2 here. What about the Fourier series coefficients of half, right? So we've determined that the Fourier series coefficients, we've determined that the Fourier series coefficients of this signal here, they are, if I compute the Fourier series coefficients of this, I'm going to get AKs e raised to power minus j k pi by 2, where AKs are given by this expression. What about the Fourier series? The question is, what about the Fourier series coefficients of this signal here? And let me call them as CKs. And I mean, so you see half is just really a DC signal, and DC signal is always periodic. You can verify very easily that CKs are going to be equal to half only when k equals 0 and is 0 otherwise. And if I plug in AKs into this thing here and from over here to over here, so these are going to be equal to half e raised to power j 0 times pi by 2 when k equals 0, and sine k pi by 2 divided by k pi times e raised to power minus j k pi by 2 when k is not equal to 0. So there you have it. And I can simplify this a little bit more. So let me do that. So x of t minus 1 minus half, which is g of t, will have Fourier series coefficients. Will have Fourier series coefficients which are equal to a k is e raised to power minus j k pi by 2 minus half times minus ck's, and this is going to be equal to 0 when k equals 0. And for k is not equal to 0, what we see is that ck's are zeros, and the Fourier coefficient of these are just this. One of the other things you immediately observe is that this is actually equal to e raised to power minus j pi by 2 raised to power k, which is just simply minus j raised to power k. So the final result that we have is that this is minus j raised to power k sine k pi by 2 divided by k pi when k is not equal to 0. So this is the final result.